Hello and welcome to ThePrint. This is Akanksha Mishra and you're watching Scientifix, where I will be taking you through this week's top science news from across the world. South Asians have long been known to include milk, cheese and dairy products in their diets. But is this a genetic trait that provides us with an evolutionary advantage, or did it happen just by accident? A fascinating new study by the University of California, Berkeley's Department of Molecular and Cellular Biology did genome analysis of 8,000 Indian, Pakistani, and Bangladeshi genomes to understand exactly how we have developed lactose tolerance. If you're not familiar, lactose tolerance is not the norm globally. Babies are born with an enzyme called lactase, which helps break down lactose in breast milk. But as people grow up, most of them lose this enzyme and are therefore lactose intolerant. The people who do not lose this enzyme develop lactase persistence in their adulthood, which includes certain European and North American populations. For the longest time, it was known that lactase persistence happened in European pastoralist communities around 5,000 years ago because they lived in very cold places with no crops or vegetation and they had to rely on dairy and meat to survive. This meant that being able to digest milk was an evolutionary advantage for them. But in South Asian communities, as the UCB researchers found, the trait did not develop for any evolutionary reasons but was just by accident. In most South Asians, the lactose tolerance enzyme only spread because they interacted with the European pastoralist. It offers no competitive advantage since South Asia was always a dairy plus crop dependent community. And its spread is prevalent even now because it was only passed down through generations. Next up, the American Geophysical Union's new study discusses the need for a new Category 6 of hurricanes as the rapidly warming oceans of the world are producing increasingly extreme cyclones. In a paper presented at the AGU's annual meeting on 19 December, researchers from the National Taiwan University spoke about how new storm hotspots are growing in the Atlantic and the Pacific Oceans, partly because of human-induced climate change. Hurricanes or cyclones or typhoons are basically storms that are formed in the sea rather than on the land, and they are categorized from 1 to 5, typically based on their intensity and their wind speed. However, the Taiwan University researchers analyzed hurricanes over the last 4 decades and found that storms exceeding wind speeds of 160 knots, which is higher than even Category 5 hurricanes, have become more frequent in the recent years. They identified 2 hotspots where most of these hurricanes were originating: Western Pacific and the Gulf of Mexico, because these areas have higher surface temperatures and warmer waters reaching deep into the ocean. Warm water is the fuel for tropical cyclones, since it creates a feedback loop that leads to more condensation, stronger winds, and more rainfall. The most important finding of the study was that at least 60 to 70% of the intense warming of these oceans is human-induced. If it continues, the kinds of storms that they lead to might need a separate category altogether, because the intensity will become too high for our current measurements. Next up, around 4.6 billion years ago, the Earth was a hostile, molten world which was filled with a magma ocean because of repeated asteroid impacts. The surface was so hot that liquid water could not exist at the time. How the planet later acquired and retained enough water to form oceans that cover 70% of its surface has long puzzled scientists. But now, a new study led by the Guangzhou Institute of Geochemistry in China offers a new answer. Earth's early water could have been locked away inside the mantle. The researchers show that brigmanite, which is the most abundant mineral in the lower mantle, can trap significant amount of water within its crystal structure, and it can act like a microscopic reservoir. The team recreated the extreme pressures and temperatures of the deep mantle in a lab, and they found that brigmanite's capacity to store water increases sharply at higher temperatures. The study suggested that during Earth's hot inferno period, the lower mantle became the planet's water reservoir, potentially holding up the equivalent of today's oceans. We finally have an answer as to how our Earth became the blue-green planet that it is today. And finally, asteroids are not just floating pieces of rocks that could accidentally collide with the Earth, they are also literal gold mines of celestial history and mineral resources. Some of these rocky objects were made during the birth of the solar system, and they might have rare metals that have been developing over centuries and could potentially even be mined for resources. The way we study what asteroids are made of currently is by studying the pieces of meteorites that fall on Earth. A new study led by the Institute of Space Sciences focuses on rare carbonaceous chondrite meteorites, which might be part of C-type carbon-rich asteroids. Now, only about 5% of meteoroids that fall on Earth are made of carbonaceous chondrites, and they are often fragile, making well-preserved samples very uncommon. By analyzing carefully selected specimens using mass spectrometry, the researchers could determine the chemical composition of the asteroids that source these meteorites. The study found that while some primitive asteroids may contain scientifically valuable material, they generally hold very low concentrations of precious metals. So large-scale mining is impractical for now. But another reason why this mass spectrometry study was important is because very soon we'll be able to collect asteroid samples directly from space. So if we analyze meteoroids and figure out the chemical signatures of asteroids in space, we will be better prepared to know what samples to get and which asteroids to target. That's all we have for you today. Thank you for tuning into The Print.